Hi friends and welcome to Geeks for Geeks. In this tutorial, we will learn how to find number of pairs in an array such that x raised to power y is greater than y raised to power x. So here's the problem. Given two arrays x and y of positive integers, find number of pairs such that x raised to power y is greater than y raised to power x, where x is an element from array x and y is an element from array y. Let's look at an example where array x is this and array y is this. So for this input, the output is 3. The pairs for which this condition is applicable are 2, 1, 2, 5 and 6, 1. The brute force solution is to consider each element of array x and array y and check whether the given condition satisfies or not. Here's the implementation of this problem in C++. Let's look at a better solution to this problem. First, we sort the array y. Now, for every element in the array x, we need to find the index of smallest number greater than x in the array y. We can do this using binary search or inbuilt function upper bound. All the numbers after this index satisfies the relation. So we just need to add the size of array of y, which we represent as n, minus that index to the count. These are a few exceptions. If x equal to 0, then the count of pairs for this x is 0. If x equal to 1, then the count of pairs is just the number of zeros in y. The following cases must be handled separately as they do not follow the general rule that x smaller than y means x raised to power y is greater than y raised to power x. These cases include when x equal to 2 and y equal to 3 or 4, because 2 raised to power 3, that is 8, is smaller than 3 raised to power 2, that is 9, and 2 raised to power 4 is equal to 4 raised to power 2. This table shows all the exceptions. We can see that at x equal to 0 and any value of y, the relation is not applicable. So we have 0 in these slots. 1 represents that the relation is valid and 0 represents that the relation is not valid. At x equal to 1 and y equal to 0, relation is applicable. So we have 1 in that slot. And so on. This table shows the result for all the values of x and y where the general algorithm is not applicable. Let's implement our algorithm on this example. We can see that y is already sorted. Starting with x equal to 2, we need to find elements in y that satisfies the given condition. From the previous table, we can see that x equal to 2 and y equal to 1 satisfies the condition. Now, the upper bound of 2 in y is 5, which has the index 1. So according to the algorithm, the number of pairs that satisfies the given condition for x equal to 2 are 2. The pairs are 2, 1 and 2, 5. Next, x equal to 1 does not satisfy this condition for any value of y. Next, x equal to 6 satisfies this condition for y equal to 1. So the number of pairs that satisfies the given condition for x equal to 6 is 1. The pair is 6, 1. So the output is 2 plus 1 equal to 3. This function returns the count of pairs with x as one element of the pair it mainly looks for all the elements in array y where x raised to power y greater than y raised to power x. If x is 0, we return 0. If x equal to 1, we return the number of zeros in y. Else, we find the upper bound and count using this statement. Here we are checking for the exceptions we discussed in the table. This function counts the total number of pairs. First, we store the count of 0, 1, 2, 3 and 4 which have exceptions. Then we sort the array y according to the algorithm. At last, we count the number of pairs for all values of x using a simple for loop and the function we just discussed. Let's discuss the time complexity of this problem. Let m and n be the sizes of array x and y respectively. The sort step takes n log n steps. Then every element of x is searched in y using binary search. This step takes m log n time. So the overall time complexity becomes O of n log n plus m log n. This brings us to the end of this tutorial. Thank you for watching. Please leave us your likes and comments in the comment section.